All right, this lesson here is called Volumes of Revolution. And together with the next lesson from section G, we're going to look in both lessons at how we find the volumes of 3D figures that have been formed by revolving shapes. And these shapes are going to have boundaries that are defined by functions and lines in the XY plane. We're going to revolve these regions around the X or the Y axis or some other line to form some complicated 3D figure. Then we want to find the volumes of these 3D figures. So this lesson, we're going to look at what is called the disk method. In the next lesson, for section G, we'll look at what is called the washer method. But before we get into this method, I think we want to just be a little bit more clear about what we're actually doing to form these shapes here. So let's start with a fairly simple example. We can imagine having a 2D shape like this semicircle right here. And we're going to take this 2D shape and we're going to revolve it around a line. So I'm going to draw the line in like that. And we've got to imagine taking this, flipping this 2D shape out into the third dimension. So it is revolved around this line. And as we do that, starting sort of from this shape like this, it's going to come out of the board, then back down into the board, and then all the way back around up to the top. And it's going to trace out a region in three-dimensional space that would form a shape that looks like this, okay, which we recognize as a sphere. Okay, so revolving a 2D shape about some axis or some line sweeps out a three-dimensional region or a three-dimensional volume in space. So if it was just a matter of forming shapes like spheres, we wouldn't bother using calculus. But what we're going to want to do is take more complicated regions, like you see in this graph over here on the left here, where we've got the upper value of this is formed by some function. The left and the right values are these vertical lines indicated by A and B here. We can imagine taking the region underneath this curve here and rotating it around the x-axis to get this complicated looking thing that you see over here on the right. Okay? So how do we calculate the volume of this thing that we have over here on the right? Okay? Now the method that we're going to use conceptually is similar to what the method that we used when we started talking about areas under curves. So when we were trying to find the area under the curve, we divided that area up into these little tiny rectangles. So we'll just draw one of these little rectangles in here. And we said that these rectangles had a width given by delta x. And we knew how big that delta x value was because it was just the region that we had to the boundaries of that region, or the range of the region, divided by the number of intervals that we had. And then we knew that the height of each one of these little rectangles was given by the value of the function somewhere inside that little interval here. So this is like f at xi. Okay? And if we multiplied that height and that width together, okay, we know that that gave us the area of one of those rectangles, and then we just added up all of those rectangles, I equals 1 to n, and we use that as an estimate for our area. And then, of course, we took the limit as n went to infinity, giving ourselves more and more rectangles to make our approximation better and better and better, and this led us into the discussion of integrals. So when we're working with volumes, we are going to do something similar. We are going to take one of those little regions, those little rectangle area elements, okay? It's still going to have a certain height and a certain thickness, and we're going to see what happens when we take that and we revolve it around the x-axis. So we can imagine starting with something that is a rectangle here. Okay, as we revolve it around, it's going to trace out a shape that is going to look kind of like this. Around like this. And then the back surface is going to do something kind of similar. And it's still going to have some thickness associated with it here. So we revolve this rectangle around the x-axis, and our rectangle traces out a region or a volume in space that looks like a little disk okay, or a cylinder. Now, rather than figuring out the area of this thing, we are going to figure out the volume of this thing. So our original rectangle that we started with always had a width of delta x, okay, and its height was given by, I don't know, let's just say the height is given by y. Okay. When we rotate that rectangle, or sorry, revolve that rectangle around the x-axis, it's still going to have, if we're thinking about this in terms of a cylinder here, we need to figure out what the radius of the cylinder is, and we need to figure out what the thickness of this cylinder is, or the height. So the thickness of the disc, or the height of the cylinder. So the height of our cylinder is going to be delta x, or the thickness of the disc, or that's still the thickness of the rectangle that we started with. The radius is going to be the height of that rectangle that we started with, that dimension right in there. So if we wanted to calculate the volume of this disc, of course, the volume of the cylinder is just pi r squared h, or in this case, our radius is y, so this would be y squared, and our height would be delta x. So we're going to apply this thinking to a problem like this. Okay? We are going to start with, one of these little area elements. Okay? Delta x, its height is given by f at xi, and we imagine rotating this around, and over in our volume picture over here, we're going to get a whole bunch of little tiny cylinders, or little tiny discs. Okay, and if we have, another disc beside, another sort of rectangle beside this one, this will form another little disc over here, kind of beside over here like this. Okay, so we can think of this 3D shape as being composed of all of these discs set one next to each other. Then to compute the volume of the shape, we just add up all of the volumes of each one of these individual discs. So how many discs do we have? Well, let's say we have n discs. Okay, the thickness of each disc, we'll call that delta x, and it's still going to be, because we're still going from A to B here, still given by B minus A divided by n, the number of discs. The height of each one of these things is going to be given by the value of the function f of xi that formed our little rectangle inside of our area there. And so we're going to have the volume for one of these discs that is going to be given by pi, our radius, squared times delta x. So this is the volume of, let's say it's one of those individual little discs there. Okay? So to find the volume of the entire shape, let's just say the total volume, we're going to add all of these up. So the sum, so I goes from 1 to n of pi f at x squared delta x. And of course, we can do the same kind of thing we did when we were working with areas. We can increase the number of little rectangles, or increase the number of discs that we have by taking the limit as n approaches infinity. And as we do that, of course, this sum that we have over here is going to turn into a rectangle, an integral. So our volume is going to be, instead of the sum, it's going to be the integral from a to b of the argument inside that sum, pi f at x squared, and our delta x becomes a dx. So this is sort of the general formula for a volume of revolution. Okay. And I'm going to put in brackets disk because each of our little volume elements that we've been using have been in the shape of a disk. So what does this look like when we apply it to an actual question here? So here's our first example. Find the volume of the solid generated when the region under x cubed from 1 to 2 is revolved around the x-axis. So the region that we're looking at is this region in here. And we imagine revolving it around the x-axis. So the formula that we developed on the previous page was it's going to be pi, integral from a to b. Pi can come out of the integral because it's just a constant. Our function, f at x squared, and we're integrating over dx. So in this case, our region goes from 1 to 2. So those are going to provide the limits of integration. Our function is just the function x cubed. We have to square it, and we integrate over dx. So we can evaluate this integral. Before we evaluate it, we might as well simplify the exponents here. 3 times 2 is going to give us an exponent of 6. So the integral from 1 to 2 of x squared, x to the power 6 dx. Our antiderivative is going to be 1 over 7 x to the power 7. And we have to evaluate this thing from 1 to 2. It's going to be pi times, let's see, if we evaluate this at 2, we get 128 over 7. If we evaluate it at 1, we get 1 over 7. So our final answer here for the volume is going to be 127 pi divided by 7. Just applying that formula. All right, so let's look at a second example here. In this example, we're going to change the line that we revolve our region around. So find the volume of the solid formed by revolving the region bounded by y equals x cubed, so the same function, y equals 8 and x equals 0 about the y-axis. So the line y equals 8 is going to be, let's see, 5, 6, 7, 8 is going to be the line right here like this. Y equals 8. Line x equals 0, of course, is our y-axis. So the region that we're looking at is this region bounded in here. And we're looking at revolving this not around the x-axis, but around the y-axis, and looking at what sort of volume that is going to sweep out. So because we're revolving around the y-axis, it's better to think to do our integral in terms of y rather than doing it in terms of x. So we are going to integrate with respect to y. So our volume formula is going to be the integral from a to b, but instead of an f at a function of x, we want a function of y, and we want to integrate with respect to y. So the function that we have to work with here is y equals x cubed. We want to turn this into a function in terms of y. So let's just isolate for x here, taking the cube root of both sides gives us x is equal to the cube root, or y to the 1/3. So this then is going to be our function of y. f of y is y to the 1/3. So our volume will be pi times our integral. Now, in this case, we can figure out the limits of integration basically from the graph. We can see that our shape is going to start down here at a y value that's equal to 0, and it's going to go up to a y value that is equal to 8. So we are going to integrate from one end of this shape to the other. So we're going to integrate from 0 to 8, and the function that we're integrating is y to the 1/3. We have to square that, and we're integrating with respect to y. And then it's just a matter of evaluating this integral. Let's simplify first by squaring it. So this will be y to the 2/3 dy. Our antiderivative is going to be, let's see, we're going to end up with a y to the 5/3. Okay, and then to cancel that out, we need a 3/5. And this gets evaluated from 0 to 8. Okay, evaluating at 8, we're going to have pi 3/5, 8 to the 5/3. And then, and then when you evaluate at 0, it's just going to be 0. Okay. So we can just work out what this is. This is going to be 3 pi over 5. If we take the cube root of 8, we get 2. And then 2 to the power of 5 is going to be 32. So this times 32. So then 3 times 32 is just going to be 96. So 96 pi divided by 5 is our final answer for the volume.